Aloha class last night. Chicago Bears 31, Washington Redskins 15. Quick reenactment before we get to the next lesson. Case Keenum Jetpacks. Swim move, Khalil Mack. Give me that football. 2 sacks, 2 fumbles. What's up? All right, here we go. Section 5.2, definite integrals. Okay, what topic are we talking about in terms of the AP exam? Topic 6.3, Riemann sums, summation notation, and what a definite integral is and notation. Okay, class? So here we go. Let's answer some questions here to get started. Okay, could you, let me get my pen going. All right. Could you determine the area under the curve from A to B for the following graphs? Faux shizzle, my nizzle. For sure, right? For that you could, right? We just do some rectangles and we're good to go. This guy here, though, it's kind of interesting because I have some area below, some area above. Can I still do that? What is our area that's underneath the curve? What do we call that? That's what we get into here in this chapter. We need a generic process, okay, for finding the sums that allow us to deal with negative values. Now I could draw a picture here, and what I want you to do is I'm going to go to this really cool website that's going to help us get a really good understanding of what's going on. I don't think I can write on this website. Okay, we'll take a quick stab and see if I'm able to. Oh, snap. I was able to write on this. Sweet. All right, so what we do is, you look, I have a curve here, and I'm going from 0 to 4, and I broke it into 4 partitions, okay? And we're going to make up some formulas here, and it's going to introduce to us what a definite integral is, okay? But I have 4 subintervals, okay? I'm going to call this the change in x1. I'm going to call that the change in x2. So what you want to do is you can draw this in the little spot that I just gave you. So I have a change in x1, a change in x2, x3, x4. And the height of the function, if I'm on LRAM, would be f of that, okay? That's the change, but it'd be like f of c1. You know, with C1 being 0 in this case. That would be f of C2. That would be f of C3. That would be, that'd be f of C4. Okay? So, right, the way I find the area of that, and you know what's interesting to notice, is the area down here is going to give me some negatives. These guys are going to give me some positives. Okay, and hopefully you notice the positives far outweigh the negatives, and thus we had an LRAM of 20 for this particular problem. Okay, but what we do is we multiply the width of each one of those partitions by the height of the function, right? And then we add up all of those guys. Now, I'm going to make this, I got this really cool website here kicking, and I love it because I'm even actually able to write on it. Okay, but I could take this, right? And the way I get a better approximation is I use more and more rectangles. Okay, and if we go back to my little page right here and I get my pen, right? You could have drew your picture right here with what was going on, but this is what we are doing, right, class? That's the height of the function. That's the width of the partition. Okay, height of the function width, and we just add all those guys up. And then we learned last class, right, the more rectangles we do, the better approximation that we get. Now, this is the concept of what we call a Riemann sum. Okay, it's a little fancy guy, and we're going to use it a little bit here in AP Calculus, but that just means you're going to sum up, okay, from k equals 1 to n being the number of partitions. So for the example we started with, we had 4, right? So that'd be from 1 to 4. You'd have 4 rectangles, right? If I had 8, it'd be from 1 to 8, and you're just going to add up all those guys, all right? That's kind of what that stands for here. Now, what I would like you to do, and I'm going to kind of go by this quickly, but I would love for you to hit pause since you're at home, or maybe you're chilling at home with your cool neighbor that is in class with you, or maybe even from a different class, but see if you can answer those questions. Or maybe FaceTime someone, right? I got homie just got dropped like Case Keenum did last night, all right? But I want you to answer those questions. I'm going to take you back after you hit pause, answer those questions, and come right back, all right? All right, hopefully you're right back at me. And if you are, I'm going to go back to this cool little Riemann sum and look at what happens. How could I get the best approximation? Booyah, look at all those rectangles. That's 33, 35, 45, and he goes, that's 100 rectangles. Oh my gosh, if I did 100 rectangles, would that give me the exact area, or would that still be an approximated answer? Think of that for a brief moment. It's 45.472. That's the area. Now that's a curve, so would that give me the exact area? Or what could I do? to get that exact area. Okay, make sure you answer those questions. If you have any questions about them, come on in class. I will answer them for you real quickly. Do the partitions have to be equals with? No. Does C of k have to be any particular value in the subinterval? A C of k can be any value in the subinterval. When we have done this process, yes, we have already done this process. LRAM, RRAM, and MRAM. Right? That website does a really cool way of doing it each. You can look at that website. Okay, boom, right? Look at that website. It's right up here, you guys. Whoa, snappage. Okay, that website's right up there. Whoa, what's going on? I guess I can't do that even if I got the pen going on, right? It's right there. Okay, but what I can do here, which is super cool, okay, is I can change those. There's RRAM. Okay, and it doesn't look too good when I'm using too many rectangles there. But that's RRAM, right, class? Boom, and there's MRAM. Okay, so this is a really cool website that you can play with and check it out. Okay, there's RRAM 80 because most of the areas are above. And remember, MRAM is probably our best estimate for that guy, okay? But let's keep on going here with notes, right, class? Let's keep rolling. Okay, but let's get back to what I was just talking about, right? What would give us the exact would actually be, let's say, an infinite amount of rectangles. How have we been using this infinite in AP Calculus? A definite integral is simply the limit. Ooh, cursive, check that out, of a Riemann sum. If you notice in step 2 above, we didn't care what the width of our subintervals were. We use the notation, this, it's called like magnitude, to denote the longest subinterval we can force, we want the subinterval really to be 0, right? The limit allows us to take it so the width between those rectangles are 0. If the width between those rectangles are 0, it's like having an infinite amount of rectangles. Once again, the idea of a limit allows us to do that. Okay, or another way to write it is from 1 to n, but n being infinity, saying we have an infinite amount of rectangles. All right, here we go. Let's introduce this guy. Here is our very, very fancy definite integral symbol. And the way we say this is the integral of f of x from a to b dx. Believe it or not, dx is your change in x. Remember, that's our width. So you have your function value, you have your width, and you have this means we have an infinite amount of rectangles. Okay? If the function is continuous, then the definite integral will exist. It's got to be continuous and able to have a definite integral, right? If not, you couldn't find the area. Right, class? Your rectangles or your area would just run through the graph. Okay, however, the converse, while true for some, is not always true. Okay, means if you have a definite integral, is it always continuous? And we'll get to those, okay, class? All right, using definite integrals as area. We can define the area under the curve, y equals f of x from a to b as an integral from a to b. As long as the curve is non-negative and integrable on the closed interval from a to b. Drawing a picture and using geometry is still a valid method for finding areas in this class. So for example 2, what we're going to do is we're going to sketch it, and we're going to see if we can use some geo to help us to get the answer. All right, class, let's put this up a little bit, and let's see if we remember how to do these guys. Let's go ahead and draw the graph. That is the graph of y equals 3. Y equals 3 is a horizontal line, and I'm going to do it from 2 to 9. What is the area? That right there. Can you find the area of that? Oh, snap, that's just a rectangle, right? And what's the area of a rectangle? The area of a rectangle is simply the length, which is 9 minus 2, which is 7, times the height or the width, which is 3. So I get 21. Units squared if you really want to have units. Here we go. Absolute value of x. How do I graph that guy? Well, that's 0, 0, 1, 1, right? It's up 1 over 1 going that way. It's up 1 to the left, 1 going this way, right, class? But I'm going from -2 to +1. And the area is from the curve to the x-axis, right, class? Boom, there we go. So I have 2 triangles in that case. A triangle's area is 1/2 the base, which is 2, times the height, which is 2, plus I've got this little area over here, which has a base of 1 and a height of 1. So what do we get there? We get a little 2 plus 1/2, so that's 2.5, right? Or 5/2. Boom, done. Here we go with this guy. Do you remember what the graph of that looks like? You need to know. Hit pause and see if you were able to draw the graph of that. That, right, class, is a semicircle. And since it's a positive square root, it's a semicircle with a radius of 3. Well, how the heck do I find the area of that? Well, a semicircle is the area from the curve to the x-axis from -3 to 3. So it's pi r squared. But what am I forgetting at home? It's half of a circle. So it's 9/2 pi, right? Are we good to go? Are we doing okay? Come in early tomorrow if you're struggling a little bit. Quick question for you guys. Is A, B, and C, are those exact areas or are approximated? Those are exact, right? We didn't have to use LRAM, we didn't use RRAM, we didn't use MRAM. But what we did do is we used geometry, and it's not a curve. Well, the circle's a curve, right? But we have a formula for the area of a circle, right? So those are all, believe it or not, exact areas, right? And that's that integral symbol means. They want us to find the exact area. Okay? All right, let's keep rolling. So what happens if the area is below the x-axis? As I mentioned before, area in the problems we just did, they were all above. Okay? Can negative values if the curve lies below the x-axis? So that's what we're going to look at right now. Can you graph that function? And let's think about it. Okay, so let's look at that graph. That would be up 3, a y-intercept of 0, 3, down 1, over 1, down 1, over 1. I get a graph that looks like that. Hopefully we realize that that is 3, 0. And I get a line. It's linear, right, class? A says, what's the area from 4 to 8? Ooh, that's 3, so that would be 4 to 8. Oh, snap. And that's below. So we're going to evaluate this. Is it going to be the exact area? It is, because that looks like a trapezoid, right? So I need to know the area of a trapezoid. Let's see if I can find the area that's 1/2 the height. Okay, what is the height of my trapezoid? Remember when we were doing these problems, these are my bases, right, class? And that's my height. So I have a height of 8 minus 4, which is 4. And then I have a couple of bases. How do I find those? Well, it's the function value, right? So what's the function value at 4? If I plug a 4 in there, I get a -1. Plus, what's the function value at 8? Plug an 8 in there to get the function value, I get -5. Oh, snap, that's 1/2 of 4 times -6. Oh, snap, that's -12. Did I get negative? Yes, so does that mean area under the curve is negative? It sure does, all right? So we can get a negative answer for an area because this symbol right here, always stands from the area. It's the area of the curve to the x-axis. Okay, class? Something very important to pay attention to. Okay, so this next example will really test that concept of negative versus positive areas. Okay, here we go. They give me this. So what they're saying is, here, I'll draw it over here because we're going to use this for this entire problem. Okay, class? That, let's see, sine is 0, 0. Then that's pi over 2 is up there at 1. And that's pi right there. So if I just draw that, they're telling me to use that information right there, that is equal to 2. And that makes sense because it's above the x-axis, right, class? All right, let's see if we could answer the rest of these questions. Okay, well, what would it be then from pi to 2 pi? Well, that would be this bottom half, right? I'm going to draw my picture. So it would be this bottom half right there. Well, it's symmetrical. Remember that word symmetrical? So if that's 2, if it's above the x-axis, it would be -2 if it's below, right? Class, try the next one. Hopefully it makes sense, okay? Oh, snap. This one here means they want me to take it the entire. That's 2, that's -2. So that'd be a +2 and then add a -2. Oh, 0. We have like no area, which kind of makes sense, right? You take that positive area with the negative area, they kind of cancel themselves out, okay? Now let's do my next guy. This one says from 0 to pi. Well, if I just go from 0 to pi, snap, I'm going to cut that bad boy off right at pi. Well, that's half, isn't it, class? That is half of that area from 0 to pi all the way to here, correct? Even though I'm not using that. So what's half of 2? That's 1. Oh, nice. Look at that. That little piece of information they gave us is allowing me to find the exact area of all these different definite integrals. All right, here we go. Let's do our next one. Oh, snap, they're making me go to some negative case? Well, that is from 0 to pi. So that would be from -pi all the way to pi. Oh, snap, that's just a little -2 plus a 2. That says 0, right, class? Easy peasy, Japanesey. All right, here, how do I do this guy right here? Well, there's actually a couple of ways to do this one. Okay, a couple of ways. I think the best way is using some integral in limit. Remember that integral is really kind of like a limit. So what I could do is I could break it up into two separate problems, right, class? So I get that, and I get this. Oh, sweet. I know this answer. That was 2. Well, what the heck is this answer? Well, that's the graph at y equals 2, right, class? And I'm going to go from 0 to pi. So what the heck is that guy's area? Well, it has a width of pi. It's a rectangle, and it has a height of 2. So my answer for this would be 2 pi plus 2. Right, class? You know what's cool is there is another way to think about that problem. It has a shift. It has a shift of up 2. So if it has a shift of up 2, that problem, believe it or not, looks like this. And it goes from 0 to pi. So it goes from 0 to pi. So you have that right there, and then you're going to add that right there, which is really doing the problem the same way. So there's a couple of ways you could have done that problem. If this was your first thought, kudos to you. It's a really good thought, and it's a really good job of using your transformations. All right, here's our last one. We'll make it in red here. We have, what is that? From pi over 2 to 0. Pi over 2, that's pi over 2. And they want me to go to 0. So it's kind of like I'm going backwards, right, class? And if I'm going backwards, my answer wouldn't be 1 like it was up there. Believe it or not, it would be -1. Could you possibly grasp that concept? How about this, class? This video is going to be done in 20. We're just going to do example 5. I'm going to show you how we use our calculator to do this stuff. It's super cool. All right, let's get my calculator rolling. That's a little algebra 2 we got kicking. Let's go y equals. Clear and clear. Let's clear this screen. Make sure you're doing it with me. I got my equation right here. It is x squared. What do we have? Minus a 2x plus a 2. Okay, and I'm going to go zoom. I'm going to always do a standard to get myself started. And there's a couple ways you could do definite integrals in your calculator, and you will need to do this. But watch how cool this is. It's like Cleo Matt going at it again. Case, give me that rock. All right. All right, let's go ahead and take a look at this. It says evaluate from 1 to 3. So we're going to hit second calc. I'm going to do this integral guy, right? Because we want to find the area from the curve to the x-axis, which would be 7. That's 7 in French. And we're going to evaluate this. Believe it or not, lower limit's going to be 1. Enter. Upper limit's going to be 3. Whoops. 3. Enter. Oh, it shaded for me. Sweet. 4 and 6. 4.667, which is 14/3. Remember, we always want fractions. Fractions are more exact, right, class? Another way you could do this, let's go second quit. Let's get out of this bad boy. Math, right? You always have the chance to actually use your calculator with graphing it, or we have some math buttons here, and we're going to use 9, finite integral. Finite integral means it's defined. It's defined from 1 to 3. Let's see if we get the same answer. Okay, for my function, you can type it back in, or I put it in alpha trace y1. So there we go, and I'm going to evaluate it. dx, that's my change in x. Booyah! Math frac that bad boy, right? Math frac it. Enter. 14/3. Told you so. All right. Practice some of these other ones, right? It's on this sheet right here. Where am I at? Boom. I got to get out of my calculator. Let's go. Booyah. See you later, alligator. And it's all right there. Practice doing some of those calculator ones. Done in 20. Aloha. Go Bears. Go Indians. Let's row. Give me them toes.